Am I audible? Am I audible now? I'll use this one. It's okay, I can use this one.
1 minute, 1 minute.
Am I audible now? Yeah. Yeah. Good evening, all. So I'll introduce myself. So I'm currently the emulation engineer at Intel Technologies Bangalore. I work in the networking domain. I work on a lot of networking accelerators. So today the topic is on chiplets, the future for computing. So it matches to the microelectronics a bit and computing. So I'll be mostly touching upon the microelectronics. Yeah, so in the past, right, so we used to have what is shown on the left, which is a monolithic chip, which has a lot of CPUs, there are some accelerators, and all of them were connected with what is called a network on chip. But of late, because we cannot have larger dice or larger chips to accommodate a lot of the computing requirements, we started getting into what is called a chiplet based systems, where we will try to combine a lot of computing components as a CPU chiplet and a lot of accelerators into an accelerator chiplet, and memory could be a memory chiplet. So there's a lot of interest in the industry, academia, on chiplet based systems, which are both 2D, 2.5D, 3D integration technologies. We'll get into some of the visuals on how those things are integrated. And we already saw how a monolithic chip is different from a chiplet. So in the monolithic, everything is in one single die, versus a chiplet, each of them are fabricated or manufactured separately in the best or the most suitable process technology node. For example, the CPU could be manufactured on a 7 nanometer, but the memory could be manufactured on, say, a 32 nanometer or a 45 nanometer. And we are manufacturing it in the most suitable technology node, but then we are integrating everything into one single chip. And what does it bring it to? We can design chiplets in the most economical way. So for example, companies like Intel or AMD or NVIDIA, right? They are good at computing chips like accelerators, CPUs, GPUs. And there may be some other company like Rambus, which are very good in making the memory chips, right? So we can take in the best of all these companies and bring out a chip which is useful for the end customer. And there are different means of chiplet heterogeneous integrations. What you see on the top left is where we are trying to split a logic into multiple sub-logics, so which we call it as a chip split, where we are trying to split the logic into multiple. That's called chip split and integration. Versus whatever is shown on the bottom is a heterogeneous chip partition and integration, where we are trying to partition the chip as all IOs are clubbed into one chiplet and all logic is clubbed into another chiplet. So if you see that IO, logic, IO is getting into IO separately and logic separately as two chiplets. And it goes through the same process of chiplet integration. And how does it help to the end customer is from a company side, right? So for example, desktop is one kind of end application, or a client. A lot of companies call it as a desktop, laptop, or a client-based systems. The second type of systems are a server-based systems, where a lot of workstations are built around. And the third one is supercomputers, right? So when a company is building it, it just has 4 different chiplets: a CPU chiplet, a GPU chiplet, a IO chiplet, and a memory chiplet. Based on how the user wants to see it, the first one is a desktop processor, where we are just integrating a CPU chiplet and a memory chiplet. versus a server processor where there is a mix of memory, GPU, I/O, everything together as a server processor. And when we go to the super computer, we have GPU, the instances are increasing. So instead of building a unified or a unique system for each of these applications, we are making best reuse. And what is finally we get into an integration of all these GPU, memory, I/O, and CPU chiplets. I have not introduced the interposer, just in a few slides we'll get into those. So again, like how the various chiplets are categorized. One is a symmetric chiplet architecture, whatever is shown. Can I use a pointer? Okay. So whatever is shown on the top left, right? So here we have 3 chiplets. All are connected to one single memory. So none of the chiplets will see any difference in the time it takes to access a memory. Versus the second, at the top right one, where we have 4 chiplets and each have their own memory. So the time it takes to access the local memory is different from time it takes to access a remote memory. So that is called a non-uniform memory access chiplet architecture. And whatever is shown as a C, the cluster chiplet architecture is a slightly higher version of, you can say, the NUMA. But here the difference is all this memory is local to the chiplet. We don't have any remote chiplet trying to access the memory. And then the fourth one is a heterogeneous, where we are trying to have a chiplet consisting of a lot of cores, and there is another chiplet which is having a lot of processing elements. You can call it as accelerators. And then there is another chiplet which has a lot of neurons or a GPU cores, right? And they're all again talking to a unified main memory. And the last one, whatever is shown in the bottom, is like a hierarchy of chiplets. So for example, you have a multi-core, which is a chiplet, and they are all clubbed together as one cluster. And then we build a system out of multiple such clusters. Right? Yeah. Yeah, so B and C is, if you see between B, you still have some cross arrows going in between here. So it means that this chiplet can still access this memory. So there is a non-uniform memory access, like say chiplet 2 is able to access chiplet 3's memory. But in this case, no, we don't have that memory sharing. So each of the chiplet yeah? Yeah. So they have, this memory can be a source for this chiplet as well as any of the other chiplets can access this. So the chiplet which has a physical connection to the memory, the latency is small, but non-uniform memory access is that. Yeah. So what are the driving factors for this chiplet, right? So for example, what is shown here in the graph is on the x-axis we have a feature size or a process technology in nanometer, and what we show on the y-axis is a advanced design cost. So when we go from one technology node to other technology node, be it the fab construction or maturing the process, right? It takes a lot of dollars. So what we can see here is when we are going from say 65 nanometer to 40 nanometer, it went from 28.5 million to 37.7 million. So, but if you see, like Moore's law or a Dennard scaling has slowed down a lot, and you can see a lot of companies really struggling to get into the angstrom scaling of transistors. It is taking, earlier the technology from one technology to other used to be like 3 to 5 years, but it is taking more time these days. So what is shown here is when we are going from say 7 nanometer to a 5 nanometer, the R&D cost has actually grown from 297.8 or 298 to 542 million, which is like almost 82%, which is pretty high, versus when it was from 65 to 40 nanometer, it was just like 32% increase in cost. So this is actually driving that we are not able to scale our devices as much as we wanted because of the R&D costs and then the process maturity things it would take. So it is driving, I mean, like in the absence of a device scaling, right, we cannot put in lot of components onto the same chip. So because otherwise the chip size would increase, and which will also result in a yield reduction. So I'll talk about how the yield will affect based on the die size. We are not able to construct larger chips. Instead, we are realizing the larger chip using a lot of smaller chiplets. Okay, so this is the area wall problem. So high performance chips need to integrate more transistors, but more transistors would result in a yield reductions. Like we don't get a lot of yield. What is yield? Yield is the percentage of good dies in a given wafer. So for example, I have a wafer of say 12 mm square or whatever, right? 12 inch. How many useful dies I can manufacture on that given wafer? So that changes based on number of dies and then the process technology, which we will see in the next slide. But we are not able to make larger chips because larger chips will reduce the yield. So we have what is called an area problem, area wall problem. And chiplet technology, by still able to get a larger chip area, but without greatly impacting the yield, right? We are still able to make large chip systems which are required for all these machine learning or whatever the AI boom that we are talking about. So at the end, all these AI workloads have to run on hardware, right? And so it doesn't come free. Whenever I am partitioning a chip, right? For example, I want to have 4 CPUs, 2 GPUs, and 2 memory sections. If I just partition into CPU, GPU, and memory chiplet, it doesn't come free. So we would actually incur additional area, and we can safely assume that that additional area is about 10%. So what is shown on the top right is leftmost, we have a die size of 40 mm cross 40 mm, and then the yield there, or the percentage of useful chips, are just 35.7%, versus the next die size, which is 20 mm cross 20 mm, the yield has improved to 75.7%. And when we go to the rightmost, top rightmost, for a die size of 10 mm square into 10 mm square, the yield has increased to 94 or close to 95%, right? So we see that progressively smaller die is resulting in greater yields, right? Why? Because a tiny component, I mean, like if you go to a LO room or the fabrication, micro fabrication chip, right? People will be almost dressing like astronauts, because even a hair, if it falls on any of the wafer, right, they have to just throw away the whole wafer or a whole wafer lot. So a small component, a small contaminant can permanently ruin the whole die or a wafer, right? So smaller, the better, right? And typically the way they used to do in the past, at least when I was studying, is they used to put an ink mark for any defective die. But of late they are using what is called a digital inking. So if each wafer will have a lot number. If you just say that lot number is this, manufactured on so and so day, it will say which are XY components or XY positions of those defective dies. Yeah. So what is shown here is like how the yield changes from monolithic to 8 chiplet design. So the blue one is a monolithic, the orange one is a 2 chiplet design, and then the green one is a 4 chiplet design, and yellow one is a 8 chiplet design. So what you see is, as the die area is going from 20 mm square to 720 mm square, right? The yield for a monolithic designing is going all the way to say 55%, right? Versus for a 8 chiplet design, it is at least 90+%. Okay. So, and I think there is some animation going on. I don't know how many can make out. So here, there are two dots which are going. So for a monolithic design, for say 360 mm square, the yield is around like 70-ish, right? But for the same, for a 4 chiplet design, it is all the way up to 90%. But We cannot compare here, as I told right in the previous slide, that we will have an overhead of at least 10%. So this 360 mm square, which can be realized in a monolithic, will come somewhere here, which is because additional 10%, or it becomes like 36 mm square to make it 396 mm square over that 360, right? So we are still better. I mean, like even if my pointer goes from here to here to make it 396 mm square, I'm still above 90%, right? So, I mean, like, but does it come free? We will touch upon that. I mean, like chiplets will come with its own complexities. Okay, what is the first chiplet? So Xilinx and TSMC back in 2013 have introduced their first chiplet. There's some animation going on, so where like a chip is split into 4 pieces, right? So they made it into 4 chiplets, and whatever is shown in the bottom, like again, is a zoomed version. So it has a lot of micro bumps. It has a lot of through silicon vias, TSVs they call, and then there are C4 bumps, which are connected to the substrate. And after that, a lot of companies, high volume manufacturing companies like Intel or anybody else, right? They're trying to do a lot of these homogeneous and heterogeneous chiplets. So when I say homogeneous, the chiplet has all components of the same type. When we say heterogeneous, it has a variety of components on the same. Yeah, so this is a 2D integration where, I mean, this used to be called a multi-chip module. It's not a very new thing. It is there from 1970s, where we have multiple chips and they're all integrated on a single substrate, right? And I mean, of late we are calling it as a 2D, but this multi-chip module or a multi-chip technology, right, is there for quite some time in the industry. Then what we have is called a 2D plus integration, where, I mean, it looks very close to a 3D stack, but the only difference is that all the connections between the chips have to go back to the substrate, and then through the substrate only they'll get connected to a different chip. Okay, so this is very close to 2D, but still the connections are happening between the chips through the substrate. We still call it as a 2D plus integration. And the next one is called a 2.5D. Yeah, so for example, if there is a connection happening between the top chip and the middle chip, they all have to come back to the substrate and then go back. I have an image which shows that. Yeah, the other one is a 2.5D. What changes is between the substrate and the chips, we got what is called an interposer. So compared with the substrate, right, the interposer can provide very high density die-to-die connections and also higher bandwidth for data communication between these chiplets. Okay. And all these interposer connections will go through what is called a, what is called a TSV, through silicon via, like between the chip and then the interposer and the substrate, whatever that dots that you see, right, these lines, we can call it as a through silicon via. And then the next one is a 3D integration. Instead of everything going back to the interposer and then connecting to the next chip, here the connections actually happen between the chips. So on the top of each chiplet, we will have a lot of bumps to connect electrically to the chip which is placed above it. Okay. Routing and via are performed directly on the chip. That's the main difference. And which connects both the top. I mean, for example, we have 3 chiplets. So the middle chiplet will have electrical connection to the top one, and similarly it will have a electrical connection to the bottom one. And they're all again connected back to the substrate. It goes through. And 4D integration, I mean, like, so it's slightly that we're just changing the orientation. So it's a 3D, but by changing the orientation, we are getting into what is called a 4D integration. Yeah. I think a better representation is shown here. This answers your question also, sir. So this is 2D integration. I mean, like everything connection is going through the substrate. But I think the image is not very clear, but there is one chiplet here, is one chiplet here. The connections go back to the substrate, and from the substrate it will go back to the other chiplet. Okay. And here we see the 2.5D. Somehow the images are not very clear, but I think the presentation will be shared with you, so you'll get to see that. And then 3D is where we are actually stacking into a 3D structure, and 4D is where we are also doing orientation to a different direction. Yeah, and a quick summary of these various packaging, right? So 2D, the chip is mounted and mounted horizontally on the substrate. And the 2D plus, the chips are stacked on the substrate and connected to the substrate by bond wires. And 2.5D integration happens through the interposer. And 3D integration, electrical happen between the chiplets only. I mean, like the electrically they are connected through the TSV through silicon via. And 4D is very similar to the 3D, but just that we are also doing what is called a substrate folding to get to a different orientation. Yeah, so this is whatever is shown on the left is a top view of a high bandwidth memory package where we have a GPU and a lot of high bandwidth memories. And if you see it from the side view, right, there is a GPU tile, and this is the 3D stacked of high bandwidth memory connected through these 3D through silicon vias. And here we have what is called a 2.5D TSVs, and then there is a bond wire, there's an interposer, there is a substrate, and then there is this BGAs which connects to the PCB. Yeah, so one of the challenges is the power distribution between the chiplets. So typically we have what is called a voltage regulator module on the PCB, and then through this power grid, when we say PG, right, in this, PG is a power grid, and through these TSVs, inter-substrate vias or interconnects or through silicon vias, the power gets distributed across all the chiplets or all the dies. And again here, to make sure that we are not losing a lot of energy in the chiplet to chiplet voltage transition, we need to do calculate the target impedance and try to do the impedance matching. And thermal management, I'm not sure how clear this image is. What we see is there is the green one is a PCB, the one above that is a substrate, and above that is a die. And the die is put in a copper lid, and then we have a lot of external cooling solutions there. Between the die and then the copper lid, we have what is called a thermal interface material, which is more like a good conductor of heat. And then we have a molding component also. So in contrast to the 2D chiplets, 3D stacked chips are considered to be better in terms of integration. They are also reduced in size. They also consume decreased power, and also significantly increases the efficiency and performance, because they are all stacked very close to each other. Data bandwidth is pretty high there. But the biggest challenge is the reliability problems are a lot more in a 3D integration. So for example, if somebody claims that we have say 55% yield after packaging a 3D chiplet, it's still a very good number versus the 95 that we have seen in the past. Yeah. So failure to resolve any of these thermal issues, because thermal or reliability issues are the most important here. So thermal failures actually account for almost 55% of issues we encountered in these 3D stacks. So there are a lot of research still to be done, and as the number of chip layers increases, we need to find solutions for increased heat dissipation. I put in some animation of how package, interposer, and then the various chiplets are integrated in a chiplet integration format. So it has CPU, GPU, AI accelerators, some programmable logic. I mean, like there will be multiple instances of such things. So what is shown is a 3D memory. 3D memory is typically stacked up into multiple. We were seeing that HBM also in the past. And then we also have what is called an I/O chiplet. So the most important thing, especially because when we say chiplet, right, we are not taking it from one silicon vendor. It can come from multiple vendors. How do each of these chiplets communicate with each other? Right, that's the biggest challenge. And one of the area which is of interest is die-to-die protocols and Universal Chip Interconnect Express, the so-called UCIe, is actually playing a big role here. Any of the die-to-die connection, right, they have two components. One is a physical layer interface, the other one is a data protocol. And from the physical layer, right, so there could be either serial interface or a parallel interface. When it comes to the data protocol, it could be a PCIe, CXL, CHI, or any of the advanced data transmission protocol layers. Okay. So I have some very high-level view of the UCIe. It's a standard which most companies are trying to use for all these chiplet data communication. So what you see here is there are two types. One is called a standard package, where all these dies are actually talking through the package substrate, die 1, die 0, and die 2. But there is something for the advanced packaging also, where there is something called a EMIB. EMIB stands for Embedded Multi-Die Interconnect Bridge, whatever you see here, right? So, I mean, along with the substrate, right, they actually build a embedded multi-die interconnect on the substrate. Okay. And similarly, what you see here is what is called a COWOS, which stands for chip on wafer on substrate. So actually, wafer is equivalent to the interposer. Okay, so this is COWS or COWOS is a TSMC technology. EMIB or EMIB is actually an Intel technology, but I think of late they are available to any other people also. And then between these various layers, right, physical layer to the die-to-die adapter, there is something called a RDI or a raw data die-to-die interface. But after that, it becomes flit aware. So flit you can consider like a package, packed data. So in the raw data interface, it just is a data stream. But when it comes to flit, right, it will have some header, some metadata, some CRC, and so many other information. So a lot of places, right, you can handle a packets than a stream of data. So because if there is some data loss on a packet, you can retransmit the packet. Versus if you're sending a stream of data, even if you lose something, you have lost. I mean, there's no way that you can recover. So that's why a lot of protocols, be it CHI or AMBA compliant or any of these, right, they use what is called a flits, so that they are sent like packets of data. Yeah, again, it is showing a UCIe 3D. What is shown here is you have a compute chiplet, there is a memory chiplet, and then the UCIe lines are getting connected to this. And then when it goes to a larger heterogeneous chiplet, right, it looks more complicated. Like we have a base chiplet, we have a memory chiplet, we have an optical connection, because a lot of times, right, we may not be just doing with a copper. We might still need to get optical connections to that. Okay, and then larger interest in, especially in this 3D or a chiplet technology, is the defects. Okay, so we need to be able to confine our defects and then detect it earlier. Okay, so that's what is shown here. And then there is a IEEE standard association also, which is trying to do a lot of test methodologies, specifications to do the testing of these 3D chiplets. Okay, from 2020 onwards, a lot of EDA tools like Synopsys and Cadence are trying to provide backend tools for all these 3D integration. So 3D IC compiler, earlier it used to be called IC compiler, but now it's called 3D IC compiler because they can handle a lot of chiplet based designs also. And later Cadence also came up with these 3D IC design solutions. These are some important books, must be interesting. Like all written by the same author actually. So John H. Lewis from Unimicron Technologies, but they are really interesting. It talks about, I mean, like much more detailed of than whatever I have spoken here. Okay, so this is that IEEE standard, what I was referring to do the testing of the three-dimensional stacked integrated circuits. Yeah. So it's already in publication, so a lot of companies are trying to adapt these technologies to test it. And yeah, as a summary, right, what are the advantages and disadvantages of this chiplet? One is a yield improvement because we are going smaller in terms of the die size. And then it also means that we can market faster and also cost also reduces. And chiplets with CPU cores can reduce silicon design and manufacturing costs because we are not integrating so many components on the same thing. So CPUs are separate chiplet, memories are separate chiplet. Okay, and also there is a thermal benefit in using chiplets because they are spread across the package. So they bring in some advantage in terms of the thermal management. But on the disadvantage side, we talked that at least 10% is an increased size of the area. So there's an additional package area due to chip partition. The chiplet bridges like the EMIB or COWS, right, will increase a lot of package costs. Okay, and they are very complex to package. And then EDA tools are not that mature to handle the complexities that we are looking for. And we cannot benefit from any of the past methodologies that we have used. I mean, we have to learn everything afresh. So the challenges are challenges or the opportunities, whatever you can call, right? So there are many in terms of the package technology. Backend is like, I mean, from the front end side, which I am working on, right? So there's not a lot of challenges. We just have to make sure that electrically we are able to transfer this packet of data. But when it comes to the packaging or backend, right, there's a lot of challenges when implementing this 3D chiplet integration. Yeah, so with that I conclude. Any questions? Yeah, they're still there. They're still there. Yeah. Yeah. So they are still there, but this 3D would require to look it from a fresh lens. Yeah. So we are still using the JTAG, boundary scan, all these BIST technologies, but just to make sure, and especially with chiplets coming from multiple manufacturers. So we are talking about the problem of die-to-die talking, but when it comes to scan stitching and other thing, right, the complexity will be manifold. And we also have to make sure that none of these chiplet manufacturers are compromising on the test coverage, for example. Yeah. Yeah. Die to die.
Who are, the different memories, different GPUs, CPUs, etc.
Yeah.
So, is there a new field of inter-chiplet communication standards?
So, this whatever that UCIe I was referring to.
You mentioned about it.
Yeah. UCIe is like trying to bring in some consortium which will drive all these chiplet manufacturers to make sure that they are at least compliant to some standards. Yeah.
Are they also being driven by IEEE or?
Yeah.
So
UCIe was originally proposed by Intel, but now it's an open standard. And they are not making that this has to be PCIe or CXL. The protocol you can use, but at least you have to make sure that these 10 guidelines or 20 guidelines that we are talking, they're there.
Okay. The next question is a bit, it's a rudimentary thing, I'm not sure. So, when you talk about this world of chiplets and integrations, etc., so the let us say system on chips, either multiprocessor or RF and so on, they don't belong to the chiplet.
No, we can have all those also on the chiplet.
Also, but let us say the standard ultra scale MPS, SOCs, etc. Are they belong to this category, or
so
are they
I mean, like
old one?
today they are not integrating all this RF along with any of this computing because this will cause a lot of interference to them.
No, I don't mean RF or, okay, let's say leave RF, but even multiprocessor SOCs, which have, you have all the CPU cores, you have interfaces, you have memories, you have everything on one chip, right?
Right.
Okay, but my point is, are they belong to chiplet
Yeah,
category?
so today what they are doing is, for example, I think one of the image I showed, right? So for a desktop, we just require one CPU, one memory.
Yes.
But that CPU, whatever I shown, is a multi-core with multiple hierarchies of memory.
Okay.
It will have like say 128 cores of ARM.
Correct.
And then multiple levels of L1, L2 or a last stage of memory. LLM or whatever you can say, right? So it has, I mean, though I showed as one diagram, but it has a stack of multi-core processors, sometimes maybe a floating point unit also, which we call it as a co-processor.
Correct.
What we are talking about is, no matter whichever it is, like for example, you call it a single core 128 instances or multi-core so many instances, they can all be one chiplet, which we call it as a computing chiplet.
Okay.
So that computing could be a simple or it could be a vector processor also. Okay. But just that partition your design into smaller chiplets to handle better, improve your yields. Okay. But it could be any, I mean, I just gave an example of memory, IO, CPU, GPU, accelerator, FPGA, but it could be anything that you can envision.
Yeah, very nice lecture. I have some more discussions, but I will talk to you offline.
Sure.
Yeah, thank you.
What platform are you using to implement all these things?
Like the backend I showed, like 3D IC compiler is from Synopsys. So this is larger challenge comes from the backend because they have to make sure that this chiplet can go and sit into another chiplet and electrically, I mean, they are not, even some disorientation will make sure that our integration is incomplete. So all these micro bumps that we are talking about have to be very carefully planned, and then even these through silicon vias are such a way that they don't cause a lot of interference. So I would say that 80% of the challenge in implementing this chiplet is in the backend. But from a front-end side or a verification or a validation that we do, we make sure that between the die to the next die or a chiplet to chiplet, they're catering to some protocol like a UCIe, PCIe, CXL. So if when from a verification or a front-end side, we just see it like a lines. But from a back-end, it looks like a lot of polygons going and then trying to make a connection with one chiplet to the another. So all tools are standard tools from Synopsys and Cadence, Mentor Graphics. Did I answer your question?
Thank you. Thank you, Ram, for delivering a wonderful talk. Even though we don't have many audience, but we have recorded, we can use it afterwards. We are uploading all the keynote sessions into YouTube of our college. So I request Professor Cliff and Satyanarayan sir to honor our proud alumni. Please.
Come on.